Hello everyone, today we are going to walk you through a completely self-contained, detailed explanation of discount factor curve construction through the bootstrapping of OIS instruments, OIS standing for Overnight Index Swaps. We will share the theory behind it and a well-designed example in Excel to illustrate that theory, all of which replicating exactly what is happening in ORE, or C++ library. So the current video is just about the theory. We will first present the general principles of bootstrapping, what it is, why it's so important, the choice of instrument, etc. Then we will dive into the mathematical formulas necessary to perform bootstrapping. The second video will be the practice part. I will walk you through an example of bootstrapping in Excel, which is actually a complete parallel implementation of the bootstrapping calculations happening in ORE. And just to be clear, it means that at every single step of calculation you can see in the Excel spreadsheet, you will find a corresponding implementation in C++ with the exact same data and the exact same results. And hopefully in the near future, we'll be able to show you those step-by-step calculations with the ORE Python library, but that's for later. We will use this video and the corresponding spreadsheet as the base for more videos about ORE, the next being about equity volatility calibration, but it will also be used to show sensitivity calculations and parametric value at risk, for example. So please give us a like if you think we are doing a good job. Please subscribe to the ORE Academy YouTube channel because that gives us the legitimacy to continue doing those videos. And if you do need to contact us, please do so through email. Also, please bear in mind that this is a sort of a snapshot of an implementation. There are many more parameters and ways to perform bootstrapping, and this case is just one example of it. So let's go. First of all, it's important to notice that we are looking at the swap market in this video. We are not using bonds. Now, what mostly determines the use of one or the other is really what you want to do with your curve. If you need to discount cash flows of collateralized trade position, the discounting needs to reflect the cost of funding of this collateral. And this is usually specified in the Credit Support Annex, the CSA. In our case, it's OIS, which means we need data from OIS quoted instruments in the swap market. If it is bonds or bonds-related instruments, the discounting needs to reflect the cost of funding of these bonds. And for example, forward agreements is going to need repurchased agreement, which we call repo, whereas spot instruments will need treasury or corporate bond yields. Saying all that, there are a few main advantages of using the swap term structure instead of the bond market one. First of all, it's more liquid and with more depth, which means the beta spread tends to be narrower and with more maturities. And it has better correlation with fixed income products. And effectively, it means that we have more standardized and more accurate data points, which itself means that we are more likely to build a curve that better represents the real world. But just to nuance what I'm saying here, this is mostly true for G10 currencies. And for some markets, especially emerging markets, the swap market might not be liquid at all, even inexistent. In those cases, you have to rely on the bond market. For the US, this statement is also not so accurate because the government bonds market is extremely liquid and with a lot of depth. Swaps have other qualities as well. There's no cash exchange at T0 because they entered at par, whereas you do have to buy bonds at T0. And there's no risk of default on swaps. There's only counterparty risk. Bonds, on the other hand, do have credit risk embedded due to the reference entity on which it is indexed, having a risk of default. So swap overall are also better hedging instruments than bonds from a cash and risk perspective. In our case, we are using specifically OIS rates, simply because it became the market standard for discounting collateralized cash flow, and they are considered as one of the best available proxies for risk-free rates. Academics think so too. Hal White, you know them. Vladimir Peterberg as well. They argue that they should be used when valuing derivatives. That's the case with this example because the end game is to price an equity option. But why is it one of the best proxies? Well, that's because the main implicit assumption of a bootstrap is that on every single date, except weekends and holidays, on every single date we can borrow or invest at a given reference rate, and the overnight rates allowed just out. There are two bits of history and context that needs to be shared. First of all, in the past, the swap curve used to be considered by a market practitioner as a sufficient proxy for the risk-free curve, and it was used to discount cash flows. Such swap curve, like the Euribor or the LIBOR, are not, however, risk-free. And this has been made very apparent since the financial crisis of 2007, with the pretty obvious widening between the overnight rates and the swap rates. And you can see that here with an example of the spread between the 3 months USB LIBOR and the Fed funds overnight rates. Secondly, in this example, we are using the Ionia. Now, the Ionia, as you may know, has been discontinued since the 1st of January 2022. It has been replaced by the Ester. Not getting into too much detail about this, but basically the Ionia didn't comply with the new European Union benchmark regulation, which came into effect in the aftermath of the LIBOR manipulation scandals. The transition took a bit of time, more than 2 years, as it started in October 2019, when the Ester data was first published. And during that transition period, the way the Ionia curve was calculated changed as it started tracking the Ester. More specifically, the Ionia was calculated as the Ester plus a spread of 8.5 basis points. You need to remember that because it will impact the way we bootstrap the curve. And the reason why we still use the Ionia for this specific example is because the valuation date of our calculation is the 24th of June 2021, so during the transition period. That's as simple as that. And actually in ORE we only support 10 currency for OIS, with the first 4 being the most developed. As you may know, bootstrapping is a procedure used to construct a zero coupon curve from prices or rates of instruments that can be found on a financial market. And whenever I say yield curve in the rest of the video, what I really mean is zero coupon curve. In some contexts they are different, but in our case they represent the same thing. Put differently, the aim of bootstrapping is to extract discount factors from market quotes of traded products. Because once you get the discount curve, you can derive a zero coupon curve, and vice versa. And it works in the following way: instrument selection, instrument pricing, instrument calibration. And then we repeat the process for each quote. Now let's look at each of these steps more in detail. First of all, instrument selections. From the list of quotes, we select the next instrument in terms of maturity, working in a chronological order, that's essential. And in our case, we will use the deposit rate, or the swap rate of this quote, as the target rate. Then we have instrument pricing. We use an initial guess for the discount factors that we want to calculate, or the zero coupon rate corresponding to this discount factor. It's interchangeable. And then we value the instrument using the quote rate and the quote maturity as inputs. At that stage, the implied swap rate of the instrument we are pricing will likely be far off from the market swap quote, and that's normal. We are going to get a final result in the next step, which is the instrument calibration steps. And why do we want this value to match? Because we work in an arbitrage-free world, which means that the instrument that we are calibrating should have exactly the same implied swap rate than the market swap rate. Put it differently, the aim of this step is to find the discount factor implied by the market quote. It is sometimes possible to use analytical formulas to find the discount factor, and we will see how to do that as well. But here we are mostly talking about the use of a root finding algorithm, which means we are going to change the value of the discount factor in an optimal way until the implied swap rate matches the market swap rate. Once an instrument is calibrated, we go to the next instrument, and so on, until we have the discount factor implied by each market quotes. Before we start looking at more advanced concepts, I thought I'll just provide a small reminder on the different type of interest rate that you will likely be faced with. First of all, the simple interest rate. In this case, it only pays interest on the principal amount, or the notional, which is represented as P, R being the yearly interest rate, and T the actual time of one period expressed in years. Then we have the compounded interest rate, also called discretely compounded interest rate. which pays interest on the principal amount, but also on all previous interest already paid. Basically, all interest paid are reinvested over time. And this is the magic of compounding interest and why every financial advisor, which always tell you to invest very early in your life. Now, this is the formula for a single period, with n being the number of compounding periods per year. And this is the formula for multiple periods, which we'll need eventually in some of our calculations. So remember it. And then we have the continuous interest rate, also called continuously compounded interest rate, which it's slightly different, and they represent more a sort of mathematically convenient way of representing compounding interest rate. It assumes that the time between compounding periods is incredibly small, let's say even smaller than a microsecond, which means that the number of compounding periods tend to be infinite. And in that case, we remind you this formula, which can be where we can express this with the exponential function. And the exponential function comes with a lot of interesting mathematical properties. And why am I mentioning all of this? Because a normal LIBOR swap uses simple interest rate on its floating leg, whereas an OIS uses compounding interest rate, with the floating leg paying the overnight on a daily basis. Which is why, as we mentioned earlier, OIS is the best available proxy for a risk-free rate, because you can borrow or invest on a daily basis, and because the risk of default from one day to another is practically zero, which makes this a type of asset almost riskless. Given that there are quite a few notations that are going to be introduced while talking about bootstrapping, and in particular regarding the dates and terms and how they contribute to the creation of cash flow schedules, I'm just going to present here a summary of it. So first of all, the valuation date, represented as upper T with a 0, also called horizon date. That's the date at which the transaction is initiated, and so this is the date to which we discount back all cash flows. The quote term, represented as lower T, lower Q as Q with a quote. This is simply the length of the instrument. Here we chose the little q to be the iterator going from 1 to m, m being the number of quotes that we have available for bootstrapping at the valuation date. In our case, we have 37 quotes, 1 deposit, and 36 overnight swaps. The next definitions are instrument dependent. First, the spot date, represented here as upper T spot, or settlement date. That's the date at which the funds are transferred, and if they are funds to transfer, of course. For the deposits, there's not really a spot date per se, because it's the same as the valuation date. For the OIS instrument, we're going to look at it's 1 business day after the valuation date. And so as the settlement date, this is the date from which or to which, depending on respectively the trade cash flows are forward or backward, from which or to which the cash flow period are created. If you look at here, T spot to Tn. Now, Tn is T lowercase n, that's the maturity date, n being the number of cash flows for this instrument. That's the date at which the trade terminates, or put it differently, that's the date at which the actual accrual period of the last cash flow of the trade terminates. For the deposit, it's T0 plus the quote term, whereas for the OIS, it's T spot plus the quote term. Now, the cash flow date, represented as upper T, lowercase I. That's the date at which the accrual period of a cash flow terminates. For a deposit, there's only one cash flow, so it's the maturity date. For the OIS, it is slightly more complicated. For OIS, cash flows tend to be yearly, at least in our case, so they reset every year. It means that if the quote is inferior or equal to a year, n equals to 1, and it means that there's only one cash flow at the maturity date. If the quote is longer than a year, then there are multiple cash flows. For maturities like 2, 3, 5, 10, 60 years, the length of every cash flow period is 1 year. However, some instruments will have maturities like 15, 18, 21 months, for example, which means you will have obviously one period which is less than a year. And given that in our case, cash flow periods are determined backwards, so from the maturity days, it is the first cash flow period when I equal 1, which is going to be less than a year, potentially less than a year. If we had been in a forward case, the potentially incomplete period will have been the last one when I equal n. And for any other cash flows, upper Ti is calculated this way. And finally, we have the payment date, which is what's going to bring a little bit of complexity compared to the more traditional academic cases. In the case of a deposit, the payment is done exactly at maturity, but for the OIS we're looking at, it happened with a payment lag from the cash flow date of payment lag of 1 business day. And because the payment are done on this date, this is the date from which we discount cash flows to T0. Now it's worth pointing out that we should theoretically write all of those dates upper T, all this upper T, with the Q particle on top of the other one, so I or N, because they are actually dependent on the quote term, but we'll remove it just to make the equation, we'll see later, a little bit easier, easier to read, so please keep that in mind. And one smaller point, it is not explicitly showed here, but the dates are usually adjusted according to a specific calendar and business day conventions. In our case, it has been set to modify following, which means that if the cash flow date initially calculated falls on a Saturday or a Sunday or on a holiday, we roll the date forward to the next business day according to the current calendar, which in our case is set to target. So that's for the following part of the modified following. And for the modified part of it, it sets an exception, which is that when you move that date forward and it falls in the next calendar month, the cash flow date rolls backwards to the immediately preceding business days. Now, let's look at the instrument valuation formula and where they are coming from. First of all, why are we using a deposit? Isn't it the title of the video, OIS Bootstrapping? Well, it's actually quite standard while performing bootstrapping to use a combination of different types of instrument, such as deposit for rate agreement, all kind of swaps of future, etc. Basically, the aim is to build the curve which better represents your need from a market more or less liquid and with more or less steps of instrument. In this particular case, having a quote with a maturity of 1 business day is quite important because that corresponds to the spot date of all the OIS that we have, and there's no OIS with a maturity of 0 days, so a deposit makes perfect sense. Now, what is a deposit? Well, it's exactly what same as when you make a personal deposit on a saving account with your bank. Basically, if you deposit 1 at times t0, it will return at time t1 your initial 1 plus some interest, the amount of interest being dependent on the interest rate set by your bank at the time of the deposit, and the exact number of days you'll let your money in the bank. And the time between these two dates is represented with a small tau, which is equal to t1 minus t0 divided by 360, as set per the day count convention. And the unit is in years. The cash flow at maturity is being discounted back to the valuation date after. If we look at this from a cash flow replication perspective, at t0 we have a cash flow of -1, implicitly discounted by 1, plus the cash flow at maturity discounted back to t0. And given that one of the main assumptions is that the NPV of this deposit at t0 should be equal to 0, we obtain this equation. And very easily, we obtain an analytical formula for calculating the discount factor implied by deposit instrument. I thought I'd also share a reminder on swaps, because OIS are a special type of swap, more specifically a special case of fixed floating swap. Now, the NPV for this type of swaps works as per this formula, and it's worth pointing out that they are very general formula, which we'll refine a little bit later. One important thing to remember in the general case is that each leg can have their own set of conventions and cash flow schedule, which is why we make a distinction between the variables determining the schedule of cash flows for example, the number of cash flow and fixed and float, and the dates marked as upper T imply by in the theta and the discount factors. So first of all, we have the position side, which is the characteristic function, which will be dependent on whether you pay or receive the fixed or floating coupon, which is going to be 1 or minus 1. Then you have the notionals big N, which we make dependent as well on small I, because some trades have notional that can evolve over time. There are swaps that have a notional that increases, we call them accreting swap, and there are the ones that have a notional that decreases, which we call amortizing swaps. We also make the notionals dependent on the leg, because sometimes that's just simply the case. Each leg can have its own notional value. The fixed leg pays a fixed coupon, which is also called the swap rate, and which is set for the whole life of the trade. That's why it's not dependent on I. And this rate is actually what we get from the market quotes showed in the slides earlier. Then we have the floating leg paying a floating rate, which means it changes for each accrual period, which is why we have a high, small I here. And the way we calculate this floating rate for OIS will be described in a second because it's not that straightforward. And just to finish on general fixed float swaps, we have the accrual period expressed in years, which represent the time between the start of the cash flow period and the end of the cash flow period. And we have the discount factor, which estimates the present value of a cash flow from the moment it is paid, so from the payment date, back to the valuation date at T0. The floating rate of an OIS is calculated as the average of the overnight rates during the coupon period. So it can only be calculated at the end of a cash flow period. If we're looking at the period from T1 included to T2 excluded, which is called the T2 period, we have the information to calculate the floating rate only at T2. And if we zoom on that period, we'll understand why. It's because we need the fixings of the overnight rates for every single business days during this period. And these business dates are represented as follows. From a formula perspective, we write lower t, lower I, the I representing the cash flow period number, same as before, lower j, the j representing the business day number during that same period. So each tij represent one business day, and ki represent the number of business days during the period ti minus 1 ti. What we want to show here is the value of investing at upper ti minus 1, a value of 1. And we see how this value compounds when invested in the OIS reference rates on each business day. So calling B a synthetic riskless asset, mirroring an investment in the OIS rates or IJ, we end up with this value at small ti2, with this value at small ti3, and so on, up to the end of the current cash flow period, upper ti. And this long equation can be reduced to this, which should start to feel familiar as it looks derived from the general multiple period discrete compounded interest rate formula that we showed earlier. And we will explain this in more detail in the next subchapter. One thing to notice, there's some sort of abuse of notation here, and which is not very elegant. I noticed that too late in the game. It is that when we look at the first period, it's actually from T spot and not from T0, which is the valuation date. So sorry about that. Now, let's not forget about what we were trying to show here, which is how to calculate the OIS floating rate from a valuation perspective. By definition, the OIS floating rate for the period I, which is noted as C float lower I, is calculated as the geometric mean of the daily OIS reference rate during that period. So basically, you take the amount you earned over that period, which is B minus the 1 originally invested, and you divide it by the time over that period. And that's the formula for the OIS floating rate. So, little summary. Up to that point, we have demonstrated the general formula for fixed floating swaps, NPV. We know how to calculate the OIS floating rate from a valuation perspective. We'll see that in the case of bootstrapping, we'll use a simpler formula derived from this one. Now we're going to dive into the characteristic of the OIS instrument which are used for this bootstrapping exercise. And you will see that we make some assumptions, some valid assumptions, which simplify greatly our calculations. The first of which is that both the legs, the fixed legs and the floating legs, have a similar cash flow schedule and a similar set of conventions. If we look at those conventions in the ORE configuration files, it looks like this, and you can see that we're not making distinctions between the legs. From a formula point of view, it means the following. The notionals are equals, the number of cash flows are the same, the cash flow accrual periods are the same, and the payment dates are the same. For both legs, we use the European target calendar. The notional on both leg is set to 1, so we can remove the variable upper n altogether actually. The business day count convention is set to actual 360, so this is actually how we calculate the actual time expressed in years. Although to be fair, we had already kind of assumed that beforehand. You can see that in the previous slides. And the payment lag is set to 1 business days. Now, there are other sort of assumptions and conventions, but those are the main ones here. So we've already seen what is an OIS. Let's look at how the cash flow schedule is created. As a reminder, there are two cases. The first case is when the term of the swap is less or equal to a year. In this case, the spot date is determined as per usual by adding 1 business day to T0. And then the maturity date, Tn, which is T1 here because there's only a single cash flow, is calculated by adding the term length to T-spot, adjusting that date according to business day conventions. At the maturity date, the cash flow are calculated in the following way. On the fixed leg, in red, it's a cash flow equal to the swap rate times the accrued period, the swap being the rate directly from the quote. On the floating leg, in blue, the cash flow is equal to the float rate times the accrued period, and we will show you how to calculate the float rate in a minute. Now, in practice, there's not one party paying the fixed rate and the other party paying the float rate. No. What happens is, if the float rate is superior to the fixed rate, the difference is paid, and vice versa. And this is the amount which is paid at the payment date and then discounted back to T0. However, for the sake of keeping the fixed leg and the floating leg separated in the formula, we'll still show it as two separate cash flows. The second case is when the quote term is superior to a year. In that case, there's a yearly cash flow starting backward from the maturity date. The spot date and the maturity date are calculated the same way as before. However, now, to calculate the first cash flow date, we remove 1 year from the maturity date, always adjusting the date based on the business day convention. And you can see that the first period will either be less than a year or exactly a year. And now that we have our two exact cash flow dates, we have the first cash flow at T1 paid with a payment lag of 1 business day and discounted back from that date to T0. And then the same thing happened for the second cash flow. And the last thing we want to do is express those cash flows into formula. So first we have the two fixed leg cash flows, and then after we have the two float leg cash flows. So when we show this in this way, and that we extend them to more than 2 cash flows, up to upper Tn cash flows, we obtain the following pricing equation for our OIS swaps. We summarize them here, and in order to simplify the fixed leg NPV equation, we can take out the fixed coupon out of the sum because it's a constant, and we obtain this equation. Now, second important assumption, given that we are in a no arbitrage world, is that at T0, the NPV of a swap is equal to 0, which means that the fixed and the floating leg should have the same NPV. And from that, we can deduce the following equation to determine the swap rate. And it's a very important equation, which we'll use, for example, in our root finding algorithm during bootstrapping. And now that we have explained both instrument cash flows mechanisms, we can expand a bit on the schedule representation we briefly touched earlier. So we will have a list of quotes on the left, which are our bootstrapping inputs. You will first notice the quote number 0, which is actually not a real quote, but we need it for calculation purpose at the valuation day. Each quote represents a specific type of instrument with the term and the Easter rate. Remember that we are building the Easter yield curve first, and then from the Easter curve that we built, we can build the EONIA yield curve. For the first quote, it's a deposit, so you just add the quote term to the valuation date to get the maturity date. For the second quote, those are OIS here, so we add one business day to the valuation date, and from the spot date, you add the quote term to find the maturity date, to which you add a payment leg of one business day to get the payment date. We already talked about all this. If we look at other examples of OIS, for example, 3 months or 1 year, the cash flow schedule actually work in exactly the same way. For terms longer than 1 year, let's look at the quote number 18, which is 18 months. First, you calculate the spot date, from which you add quote tenor to find the maturity date, and from which you can find the final payment date. And nothing new so far. We've seen that. However, remember that the cash flows are created in backward way with a yearly frequency. So because here our tenor is superior to 1 year, we have one intermediary cash flow, which is 1 year before the maturity date, which means the length of the first cash flow is actually 6 months. And then you need to calculate the payment date for the first cash flow period. From then, if you increase the length of the tenor, let's look at the 4-year example, you increase the number of cash flows. And here you have 4 cash flows. And if we look at the longest tenor, 60 year, we have 60 cash flows, which is just showed here with the 3 dots. And just so that notations are clear, you can see here the quote term with a small t going from 1 to 37 or small m. And for each of these quotes, we have a specific cash flow schedule with the cash flow schedule dates marked as upper T, iterating from 1 to little n, which is the maturity date of the quoted instrument. Now we have pretty much all the elements needed to finally demonstrate the bootstrapping mechanisms. And we already have a formula for the OIS floating rate. However, like we said previously, this is only for valuation purpose. This is when you want to calculate the price of a swap. But when performing bootstrapping, we already have this price. It's actually the input in our calculations, that or the swap rate. For bootstrapping purposes, we actually don't need any information about the projected OIS rates. What we want is to extract the implied discount factor, or zero rate, from the market quotes. So what we eventually need is to find a way to express this floating rate with discount factors. Remember this formula? The one which is used to calculate the future value in an investment compounded over multiple periods? We are going to show you how this expression is used in the calculation of the OIS floating rates and how to repurpose it to show alternative ways of calculation. So let's make some rebranding and replacement. First, the future value indicates the future value of a synthetic asset marked as B. We also discretize T from T0 to Ti, and the principal now means notional. So far, so good. Now, one concept which might be slightly less trivial is that, well, the overnight rate might compound every day. So Tj is set to 1 over 360, and n, being the compounding period of the rate Rj, is set to 360. The swap instrument usually settle only on business days. So Kt, which used to represent the number of compounding periods over t, is now marked as Kti and represents the number of business days between T0 and Ti. The iterator, small j, represents a single business day, and the overnight rate become an OIS rate, noted ROISJ, adjusted for the compounding period between Tij-1 and Tij. This might be slightly confusing, so to be clear, I'm just going to give you a small example. If the overnight rate on a Friday is equal to 1%, the value obtained on the Monday is not going to be 1 plus 1% divided by 360 power of 3. It's going to be 1 plus 1% times 3 So with an effective rate of 3% divided by 360 power of 1. You can also see it differently and think about it from an adjustment of not the rate, but on the number of compounding periods per year. So instead of being 360 days, it becomes 3 divided by 360, so that's 120, because there's 120 periods of 3 days during a year. I hope that's clear. Once you've performed all this replacement, we obtain this equation, which is very similar to the equation that we established before. However, this is equivalent to representing the forward rate from t0 to ti, where this equation shows the forward rate from ti minus 1 to ti. To link the two, we differentiate the product between ti minus 1 and ti by first differentiating the number k. And then we replace this first part of the equation by b from t0 to ti minus 1, leading to this equation. And obviously to this, which is exactly the formula from before. Now, the last part needed is how to introduce the discount factor into all of this. And we remind ourselves that we are in a deterministic arbitrage-free world, which means that an investment of 1 at t0 should have a fair value of 1 at t0. You get that fair value by discounting your future value by the discount factor df, and so we obtain this equation and then this one, which you can then insert here and here. And this is how we get these equivalent formulas. But this one is the one we need. So going back to our OIS floating rate calculation, we rewrite it this way. And just a small aparté, the floating rate can also be expressed this way when equating the overnight rates to the short rate, which is pretty convenient mathematically speaking. And this approximation is actually industry standard for representing daily compounding rates. And we are getting to the end of it, I promise. At that point, the NPV of the floating leg can be expressed this way. Now, we have two cases. The first case, the trivial case, let's say, and probably the one you see most often in literature, it is when there's no payment lag. So both TI and TI pay are equal. In that case, we do a simple replacement from which we can obtain this expression, and given that all term cancel all previous term in this expression, except for the first and the last one, and given that the discount factor at t0 is 1, we obtain this very simple expression. Then you have the second case, which is more the real-world case, where there is a payment lag. The payment date happens after the date at the end of the cash flow accrual period. And we're going to keep it this way for now. Now back to the trivial case. Here we are going to be able to express the discount factor of an instrument from the maturity date Tn in function of variables whose value we already know. Remember, we have all information up to n-1. The only unknown is the discount factor from Tn. So given that both legs needs to be equal, that's our starting equation, we have this equation, NPV fix equal NPV float. Very simple. Extracting the last iteration from n, from the sum, we get this equations. And reordering everything, we obtain this nice little analytical formula to calculate the discount factor for an OIS, using only information already available. The swap rates directly from the quotes, the theta's completely deterministic, and the discount factor up to n-1, which is an information directly or indirectly when you interpolate, calculated at the previous step of the bootstrapping. And just as a side note, when there's only one cash flow, we retrieve the value of a deposit. And now the grand finale. The most common technique used to find all discount factors, or zero rates, at each step of our bootstrapping is a root finding algorithm. The objective of a root finding algorithm is to find the value x, also called roots, such that fx equal 0. We can only use this type of numerical algorithm when a function is continuous, which is the case for the discount factor function because it is equal to exponential of minus rt, which is a continuous function. We're not going to explain the actual root finding algorithm in details here. I think the video is long enough as it is, and there's sufficient documentation available regarding this type of algorithm. Just a few examples. You've got the bisection method, Newton-Raphson's second method, Stevenson's method, the inverse quadratic interpolation method, etc. They're all different in terms of complexity, conversion speed, computational need, etc. In ORI/QuantLib, we use the Brent algorithm, which is actually a combination of the bisection method, the second method, and the inverse quadratic interpolation method. It's very fast converging and robust because at each iteration, the algorithm decides which method is the most appropriate to use. So, pretty smart. In our case, we want to find the discount factor from the payment date to T0 such that the value of the swap is 0. Put differently, so that the value of the floating leg equal the value of the fixed legs, or equivalently, such that the estimated fixed rate from our calculations equals the quoted fixed rate. And that's an equation that we already established previously. So we have this equation. And because we work with algorithm, and given that it's pretty hard actually to demonstrate that an exact root always exists, or that it can actually be found within a reasonable number of iteration, we actually set a level of precision that is satisfying to achieve, which is represented here by an epsilon. So a problem become this, and this is actually applicable to any fixed floating swap, not just OIS. And at that point, you might ask yourself why the discount factor from the payment date and not from the maturity date? And that's a very valid question, which we are going to answer in a second. First, let's dig into this equation a little bit. Similarly to the analytical case, we can differentiate the cash flows between the ones at maturity Tn and which is here, and the one up to maturity Tn minus 1. And the variables in yellow are the values we were trying to estimate at that point. We've got the discount factor from the payment date, but we need to expand our floating rate, which we know how to do at that point, because we know how to express it using discount factors. And the only one we don't know is the one in yellow here, the discount factor from the maturity date. So at that point, we have what looks to be a problem with two unknown, but that would be forgetting about the power of interpolation. And more specifically, we use log linear interpolation in the case of discount factor, which means we do a linear interpolation on the logarithm of the discount factor, and you can see it here. Now, there's a lot of different types of interpolation, and here you can see just a few that we have available in ORI. The advantages and drawbacks of each of them and their typical use definitely deserves another video. However, just one thing, we want that the type of interpolation chosen to conserve arbitrage-free properties. It's very important. So we use this general equation, which when you replace the x by upper T and y by df, looks like that. And with these equations, we can express the discount factor from the maturity date with the discount factor from the payment date, which means we don't have two unknowns anymore, but only one. And mathematically speaking, we could have done it the other way around and express the discount factor from the payment date in function of the discount factor from the maturity date. But we would have had to perform an extrapolation instead of an interpolation. And even though both are using the same formula, the principle is quite different. Interpolation is used to estimate a missing past data, whereas extrapolation is used to make predictions based on past values. And interpolation is usually delivering more valid estimate, which is why we use it here, and which is why we would express any missing discount factors in function of the discount factor at the latest date possible for the current instrument. And here it's the payment date. And just to get a bit more insight about how this interpolation process works in the context of bootstrapping and root finding algorithm, let's look at this graph. Up to Tn minus 1 in orange, we already know the discount factor's value for these dates. And what we're going to do is first provide a guess for the value of the discount factor at the payment date, TNP. The guess value depends on the type of root finding algorithm that you choose. And if you remember this diagram, we are here. From this first value, which normally is not a root, we can estimate the interpolated value for the discount factor at maturity. Then we start the calibration stage with the use of our root finding algorithm. We're going to try different values for the discount factor until we find one which is going to fit the objective criteria. Now, back to where we were, we've got now a full picture of the equations necessary to run a root finding algorithm with a single unknown, the discount factor from the payment date. And then we go to the next instrument, and so on. This is the principle of the bootstrapping. We calculate the implied discount factor from each quote in a chronological order. And I'm just going to show you a small table to summarize what bootstrapping is. So first of all, at t0, we know that this discount factor is equal to 1, so that's a known information. Given that information, we can calculate the discount factor for the first instrument, which is actually a deposit. To calculate that, we can use an analytical formula, we can use a root finding algorithm. In ORE, and probably in a lot of pricing libraries, you always use a root finding algorithm. It's just easier to do so. So once you've done that and you calculate the discount factor at T1, T1 being also the spot date for the rest of the OIS trade, you can tackle the first OIS instrument. And then using this whole set of equation, calculate the discount factor at the payment date of this OIS instrument. And then you do that for the next OIS instrument and so on until you get the discount factor from every single instrument and your yield curve is constructed. Now, there's one last piece of information regarding the Ionia curve. Up until now, we have worked with Easter rates and calculated discount factors. So the first thing we obtain is the Easter discount factor curve. To get the Easter yield curve, we very simply calculate the rate implied at each upper TI with this formula, and we obtain the yield curve. Now, remember that our valuation date is 2021, and we don't want to use the Easter curve to discount the cash flows of our trade. We want to use the Ionia curve, which at the time was a Z-spread curve with a parallel shift or spread of 1.5 pips over the Easter, which we can calculate very simply like this. And once it's done, we simply have to transform the yield curve into a discount factor curve. And voila! Here is our Ionia discount factor curve. Now, this is not the case here because you only need your Ionia and your Easter curves. But in other situations, building this discount factor or yield curve is only the first step needed to build other curves. For example, in the video where I show you how to parameterize the configuration files that you need when the collateralization currency is different than the currency of the trade. In this particular case, we first bootstrap the USD Fed funds, which is also using OIS instruments. Once this is built, we can bootstrap the next curve, the USD LIBOR 3 months, which uses the first bootstrap curve as its discounting curve. And then independently, we also need to build the Euribor 6 months and then the Euribor 3 months. And then finally, once all these curves are built, you can finally build a cross-currency curve. So you see, bootstrapping is a sort of stepping stone process. This concludes the theory part of this video about bootstrapping. In the next video, we will walk you through a complete example of bootstrapping in Excel to illustrate the theory, while making parallels to how it's done in ORE or C++ library. Thank you for watching. Don't forget to give us a like and subscribe to our channel. I will see you in the next video. Goodbye.